6 essential pillars, if we understand them, will deal with integration with complete ease in the world of engineering. The first point, the definite integral from a to b, represents measuring the area between the function's curve and the x-axis, from point A to point B. This is what's meant in the world of integration. The second point, measuring the area under a curve, is very difficult, so we can divide this curve into small rectangles. And the more we increase the number of rectangles, the more accuracy we get in calculating this area between the function's curve and the x-axis. The third point, what does area mean? We look at area from two perspectives, either a geometric view, where it's a space and can never be negative, or we look at it from the integration standpoint, where it can be negative or positive depending on the effect. The actual or physical meaning of the integral is a summation of accumulations. For example, if we are now heating water, we are heating it continuously with this function. Every point matters, but the final effect is the summation of these points at each moment, or the effect at each moment. So we sum these accumulations, and that's why the area between the function's curve and the x-axis matters to us, because we sum it. And this is the goal of integration. So, if we see accumulations, integration should come to mind, and vice versa. If we see the integration process, we should ask what things are accumulating that we're calculating. The fourth point is integration, an evolved form of multiplication. If you look at multiplication here, for example, if we are calculating this area, we use multiplication, which is length times width of the rectangle. In multiplication, we are repeating the same effect or the same number several times, whereas in integration, we are repeating or summing different effects. So we are summing, let's say here, for example, the areas of different rectangles. So we can view integration as an evolved multiplication process, because in multiplication, we repeat the same number, whereas in integration, we are summing different numbers. The fifth point, the relationship between a function and its integral function. Here we have a function fx equals 3, a constant function. So we expect its integral function to be the accumulations of the area here, as we agreed. Here it's the area of a rectangle. So if we reach here, 3 times 1 length times width will equal 3. If we evaluate the integral function at 1, we'll find it equals 3. The same thing if we go to the end here, for example to 4. We know the area here is 3 times 4, 12. If we evaluate the integral function here, we'll find it equals 12. If we reach the required accuracy, it will equal 12. This is the relationship between a function and its integral function. The sixth and final point, the integral or the area is a set of accumulations that may be positive or may be negative. If these accumulations or the area are above the x-axis, in this case we're filling the tank because the flow function is positive. But if the flow function becomes negative, it's as if we are drawing water out, meaning the effect will be reversed and the tank will decrease. And this is the secret behind the positive and negative signs of areas in the world of integration.